This is a video I've been wanting to do for a while. I was given this about 6 months ago by a coworker who was giving it to him as this is a worn out 0 to 100 residual gas analyzer. This was in a piece of semiconductor equipment, and you might be able to buy something like this off of eBay for about $400 in a non-refurbished state. I do know that this system has been refurbished at least once before, and it is probably well past end of life and not worth refurbishing. So while it looks really clean, my coworker said that it probably is not and is coated with crap on the inside because it was inside some kind of semiconductor equipment. So this is a labeled Inficon, made in USA, naked residual gas analyzer. So what this is usually used for is for detecting leaks in a high vacuum system, where you want to know what kind of gases you have inside a system, or maybe you're doing some kind of process control and you want to see your ratios of different gases. You could do it that way as well. But here's my understanding of fundamentally how this works. Up here in front, and then this is just inside, this is not a glass tube, this is just a plexiglass carrier, so it's actually open to atmosphere here. Up here in the beginning, you have an ionization chamber, basically. So my understanding is that this right here is an ionization chamber. You've got a series of focusing lenses. I think these are just standard electrostatic focusing lenses. And then in this area here, this is going to be a quadrupole RF mass spectrometer. And then in this section right here is going to be an ion amplifier. And so I really want to kind of see how all these things are built and what they look like. So the biggest interest to me is going to be this quadrupole mass spectrometer right here, which should be, I believe, 4 parallel bars that are charged alternatingly, so that when an ion is accelerated through here, only ions of a certain mass will actually match the frequency as they go around in a circle, kind of a spiral pattern, down the column and into the detector. And if it's off frequency because the mass is too high or too low, and it won't make it to the detector. And you fix this frequency of this mass spectrometer and then vary the potential or the acceleration voltage here to speed up or slow down and match the atomic mass to the frequency of the RF mass spectrometer. So and then this is kind of like a photomultiplier, but instead of being a photomultiplier with a bunch of cascading little what are called diodes, they're specially coated. So there's a special coating on these that will then perform ion amplification. So let's get this thing pulled apart. So this is a conflat. I believe this is a ISO 50 conflat, maybe a 63. So yeah, this is just a little plastic acrylic carrier. And so this is what's called a naked gauge, in that this would be in the chamber fully exposed, as it is right here. So we've got these ceramic, what I want to do is I want to keep these ceramic tubes. I think what I'm going to have to do is start by pulling apart the top pieces here where these wires come in. So I'm going to save all the hardware for this as well. This jar. All right, so now I'm not wearing gloves or anything. Like I say, this is not a salvage operation. Anything I reuse from this is going to have to be thoroughly cleaned anyway. Oh, boink. Okay. Oh, I must have loosened this one when I was testing out what size Allen wrench to get. There we go. So I think these two here are going to be your ionization filament. So any residual gas in here is going to get ionized by this little cage here. And I'll see if I can't get some close-ups of some of these things as well. All right. Now what I can do, hopefully, is salvage mostly I want to get these pieces out of the way as well so that I'm not worried about breaking the dang thing. All right. One more left to go, or two more. Get these two guys out of here. I think I might have to cut these. Oh, this will be easy. Just flex this thing back and forth until it breaks. And up goes the weasel. I don't know how they would have welded that. I think they must have made this lead and then brazed it or soldered it or something onto here. And I'm going to keep this base here as well as an electrical pass-through. I want it for future use. Oh, it looks like there's a little bit more ceramic down here. There's probably a bias for the ion multiplier or something, I'll bet. Come on. Well, that's one way of doing it, I guess. I'll worry about that later. All right. I can just take this guy and I'm loath to do anything too drastic, but it comes right off. Dink. There we go. Now we have a fully, let's get rid of these little finger pin cushion makers here. Let's come right off. All right, so now the big question is how best to disassemble this bugger. Let's get a good close-up of what this thing looks like. So in here you can kind of see what looks like a grid cage, and there's a filament in there, so I think these two wires are going to a filament that goes around. Kind of wish what I could do is take this whole piece off and just disconnect it. I'm just curious. Let's see what happens when I take these three standoff screws off. Very carefully. Okay, so this is your filament right here. So this is a heater filament. Coming in, it looks like these are a little ceramically insulated and two plates bolted together. I'm guessing there's a sandwich where this thing, oh, okay, so what they did is the way they manufactured this is there's two plates here, and so this grid is welded onto this top plate, and then they just screw the two plates together. So I'll save that for right now. Let's take a look at this portion here. So it looks like there's, you can see here, this is welded onto this plate down here. And there's a hole, you can see all the residual crap on here. I'm guessing that this is kind of like an acceleration anode. You know, kind of captures some of those ions from the filament and brings them in, and they then accelerate down through the holes there. And then this is then an electron stack. So we've got this plate right here was a wire, this top plate here was a wire, and this middle plate here was a wire. So basically each of these three plates, this one here, this is middle, top, and bottom. Each of these plates could be independently biased to form an electron lens. So each of these are going to have a hole through the middle of them. So if I just undo this, I'm going to save those, definitely. Okay, I see how they did that. So you can see we've got a bunch of ceramic washers here. So this is the top plate. So the mid plate, this is your aperture here, probably a focusing or a crossover point, and then a final acceleration path. So those are cool. Let's set those aside. But I definitely want to keep all these little ceramic bits, because these are great for creating stacked sandwich layers for ion lenses and stuff like that. So all right, so now here's the fun part. So this is your RF quadrupole here now that we can see. So what they're going to do is that two of these things are going to be attached together, and the other two of these, there's going to be an RF of field potential applied to each of these across these two. So let's see if I think, yeah. So these four nuts here are just holding this outer ring in place. So this is just a machine spacer. So if we look down the center bore here, there's a ceramic insulator here, and it's just friction fitted in except for this one spot right here. So there's, if I undo this nut, dink, it's drilled into the ceramic. There we go. All right, I think I should be able to remove this shield if I get rid of these right here. And so the two bars that are coming into here, those are probably the RF feeds. So there's one here and one here, and I'm betting they go across. Oop. All right, this is the entire RF quadrupole. And bedding. Really loosen things up just by releasing that little clip that was here. Yeah, I was right. So here's your cross connects. So this right here is connecting this top bar to this bar, and this one's connecting this bar to this bar. So these two are basically one polarity, and these two here the other polarity. Charge these guys with RF, and you've got yourself an RF quadrupole mass spectrometer. That's the business end of it right there. And these are just probably stainless steel bars. They're hollow tubes. And yeah, that's real cool. I'm going to save this whole chunk as it is, because I don't feel the need to take that apart any further. This feels like a good heavy piece of stainless steel. All right. So all that's left is there's a single wire coming into this stage right here, and this is going to be your ion multiplier stage. And I don't see anything here that I can pull off other than these four Phillips head screws. Uno, dos. Oh, there's 3 screws. Okay. This whole thing just came loose on me. 3 screws. Let's see what's in here. Oh, well, that's interesting looking. What the hell? I was not expecting anything like this. Huh. Okay, I was expecting something more like a photomultiplier diode, but this is totally Galileo Channeltron. Okay. And this looks to be welded onto here. It's either welded or soldered, and it looks like it's probably TIG welded. And so it's got the ceramic insulator. It's going up to here. So this is probably some sort of acceleration grid. And I don't know what to make of this. I can't tell what's there. I'm going to have to remove this shield here. Whoa, check that. That's some vacuum engineering there. All right, so if you can see what's going on here, is they've cut a slit down the edge of the threads and the head of this screw here. This is a vacuum safe screw, so what this is doing, it's preventing any pockets from forming inside here. So what they've actually done is gone through a flat. So what they've done is they've cut a slit down to the minor diameter of the threads and kind of flattened it out almost, and just hacked it down here so that if there's air or gases trapped behind this, they can vent back out. So that's what's going on there. That's neat. Oh, interesting. They just did it straight into the screw on that thing. Huh. I think what I'm going to have to do, a little violent here. Dink. There we go. Ceramic tube. That's a finer ceramic tube than the last one. And then what I should be able to do is just pop this guy out. Dink. Oh, there we go. Now we can see what's going on here. Okay. I'll save that for later. Okay, so this is just a spring contact. Oh, this is a little... Okay, so if I... out you come. Okay. Interesting. Okay, we'll look at this in a second. That's just the base. Stay there. And this is the interesting, this is the guts of it. This is the detector here. One of the things I was originally expecting out of this electron multiplier was a discrete dynode. So what I always thought was a dynode are these little curved pieces here where an electron would bounce off, produce 3 or 4, double, 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 all the way down the line until you get this big stream of electrons. However, through this teardown, I have now learned that what exists is called a continuous dynode, where instead you have a tube that the electrons enter and then bounce off of this in kind of a curved fashion. This is the Wikipedia article on electron multipliers. I highly recommend reading it. I'd read this before, I just never thought about much this continuous dynode. So this is actually also commonly known, I guess was the original trade name is as a channeltron. However, I guess its generic name would be called a continuous dynode. So that's what we're actually seeing over here. So this is the actual channeltron that I pulled out of the RGA. And the actual continuous dynode is this piece right here. And I guess this is carbon coated on the inside. You know, it's got a special coating on it basically. And there's a few things to note about this that I didn't originally note when I first did the teardown. So this screen right here, just get in real good and close. This screen right here, this is all screen is attached to this body, which is, assuming is ground or some negative, you know, body potential. This is isolated. So there's a little mounting bracket here, a ceramic isolator, and the plate that is inside of here is actually is not connected to this. There's a plate behind here that is electrically insulated and it comes in through here. So I'm assuming that an ion stream is going to come in this way. So this was sitting in the chamber here like this, right? And if we look in there, you can see the grid from the perspective of this right here. So our stream of ions, and I want to say they're ions, they're not electrons, but I'm assuming that there is that this is basically acting like a scintillator. So an ion crashes into this and then spews off a secondary electron accelerated by the potential of this. So this is all connected here. Okay, so you can kind of see this is where that bias wire was hooking up. It was hooking up to one of the screws that was attached right here. And then there is an insulator here. And I'm assuming this is like maybe a static discharge, like a gas discharge tube or something. Maybe there's a radioactive source in here for all I know. So I have a Geiger counter, but it's not going to, you know, it's out of something like this, it's not going to detect anything out of that, especially not with this cheap piece of crap. Turn that off. My assumption is this is an anti-static mounting here, so I assume this is kind of like an air gap, electrically isolated. This is just for rigidity, so this is a little ceramic insulator, but it doesn't actually go anywhere. It just terminates into nothing. And it holds it up, and it punches through this little area. And if you look in real closely, there is a burn spot here on this plate. So this is all, once again, this is all just springy because this is our lever point right here. And this is where it actually contacts the center pin of the output was right here. So this was the output. So anyway, this is a continuous diode, not a specific individual diode like I was originally anticipating in a photomultiplier tube. Interesting stuff. So we'll keep that. I'm going to put that in a special spot. As for the rest of all this, this is just a connection. So I'm kind of guessing that, yeah. So this can all be reused, I think. So if I ever want to put an RF connection through into a high vacuum, we've got the conflat. There's a nice sharp edge for a copper gasket. I'm getting some of these copper gaskets on order. And a good 8, 9, no, 8. This one's a blank right here. We've got 8 connections through plus an RF connection. One could do a lot with this, something like this. I'm kind of guessing that this will screw. Oh, yep, that unscrews. And there's a copper pin on this. They've just soldered on the end of this that goes down onto the coworker lead through the ceramic through path. That's cool. Oh, cool. I've got myself a pass through, and I've got myself some ceramic long wire insulators. Anyway, that is a residual gas analyzer. I think these are things were probably made in the 90s. There's probably more compact versions out there, but this is the one that I had. So thanks for watching.